Let's start from here. If you remember, delta ij, this is equal delta ii is equal delta jj. You see, because this delta ij is a second order tensor, delta ij is a second order tensor, but this is a scalar. Why is it scalar? Because I is dummy and j is dummy. So I and j are dummy indices. Now this, you see this j over here, delta I, okay, remove j and put I. Or delta ij, remove I and put j. So this is sum. This will be equal to 3. Because it's delta 1, 1 plus delta 2, 2 plus delta 3, 3. Now let's see this over here. You see, delta ij, delta ik. So this will be delta jk. Delta jk. Now delta jk. You see, here is delta jk. Why? Because you see here I and I. So I remove I from here and put j. So delta jk is the same what you did before. So j is dummy and k is dummy. So this is also equal 3. Now delta ij is a symmetric second order tensor. And epsilon ijk is a skew-symmetric third order tensor. Now let's do this. You see, delta ij, I remove I and put j, so this is equal epsilon jjk. Now jjk, do you remember? Epsilon 1, 1 is 0, epsilon 2, 2 is 0, epsilon 3, 3 is 0. So this is a dummy index. This will be 0. Now let's do this one over here. You see, look. This is equal. You see this k over here? I move once, move twice. So this is equal epsilon k ij. See, k ij and k ij. So let's put over here. You see, k is dummy, I is dummy, j is dummy. So this is a number, this is a scalar. Let's sum first on k. So epsilon 1, 1 ij, epsilon 1 ij. Now let's see. You see, now for k is equal 1, okay, now let's put for k is equal 2, epsilon 2 ij, epsilon 2 ij plus epsilon 3 ij, epsilon 3 ij. Now let's see. Now let's sum on I, okay. Now I is equal 1 will be 1, 1. See, for I is equal 1, this will be 0. This will be 0. Now for I is equal 2, this will be 2 and 2. So j must be only 3. So let's do this. Let's see, let's call this 1, this is 2, and this is 3. See? Let's work on 1. Look. Now it's epsilon 1 ij. Now let's do I is equal to, this is j. Now I is equal to, this is j. Plus I, in this case, this is still, this is 1 over here, 1. Now I will be 3, and j, epsilon 1, 3, j. Let's see. This is equal. Now, here j must be 3. If j is different from 3, this term will be 0. So this will be epsilon 1, 2, 3, epsilon 1, 2, 3, plus here j must be 2, because j is equal 1, this is 0, j is equal 3, this is 0, plus epsilon 1, 3, 2, epsilon 1, 3, 2. Now, epsilon 1, 2, 3 is plus 1. Epsilon 1, 2, 3 is plus 1. So this is equal to 1. Now, epsilon 1, 3, 2. See, remember, see this 1, 2, 3. You see, look. 1, 2, 3. Now, epsilon 1, 3, 2. You see, 1, 3, 2. This is minus 1. Minus 1 minus 1 is plus 1. So this is equal to. Now, for this term 2, also it will be 2. For this term 3, also be 3. It will be 2. So the sum over here will be 6. Just easy. Now you do for the term number 2 and the term number 3. This will be, in this case, let's put here 1 plus 1. So this is 6. Now, this is an important point over here that I'll make. Let's write this equality right here. Now, you see, AJ, AK, this is a symmetric because I can exchange K and J right here. It will be the same, you see. Now, epsilon IJK, epsilon IJK, AJ, AK. You see, this is a vector. This is I over here, the free index. So this is equal. Now, let's exchange J and K. You see, right here and right there. So this is epsilon K. Let's put IJK here. Okay, let's remain I the same. This is KJ, AK, AJ. Now, this quantity over here is exactly the same as there. So, and this over here is minus this, because you see, I move just once. So this is minus epsilon IJK. This is AKAJ, so this AJ, AK is the same. Now you see, look, I have a quantity equals minus, this is equal, see, equal and equal. See, this is equal, minus, equal, minus. You see, I have a quantity which is minus the same quantity. So this implies that this equality will be 0. Now, a skew-symmetric times a symmetric matrix, you see, this is a third order tensor, is skew-symmetric. This is a second order, this is a third order tensor, skew-symmetric. This is a second order tensor. So if I exchange K and J, the symmetric part will be the same. So this is symmetric and this is skew-symmetric. So the product will be 0. See, this will be 0. Because the quantity equal minus the same quantity, this quantity over here must be 0. The quadratic form, you see the quadratic form, Aij x sub I x sub j is unchanged if Aij is replaced by its symmetric part Aij s. Now, attention here, any second order vector, a tensor in this case, is equal. You see, this is my 1/2 of Aij plus Aij. You see, obviously, okay? Aij plus Aij is 2 times Aij. 1/2 times 2 times Aij will be Aij. Now, I'll put 1/2 of Aij ji minus 1/2 of a ji. You see, now I can combine these terms put in here. This is aij plus aji plus 1/2 of aij minus aji. See, look, I decomposed aij. This is plus 1/2 aji minus 1/2 of aji. So this term here can cancel. See, this term here can cancel. This is 0. And this is aij. Now I combine, you see, 1/2 of aji, 1/2 of aij I put here. So plus 1/2 of aij minus 1/2 of aji. Here you see clearly that this is a symmetric part, because if I exchange I and j, this term remains the same. Not here, because if I exchange aij, there's a minus aij. So this is a symmetric part. Let's put here aij is equal aij symmetric plus aij is skew-symmetric or anti-symmetric. This is a symmetric part, this anti-symmetric part. But you see xi, xj are the x coordinates. So x1, x2 is the same as x2, x1. So this over here is a second order tensor, okay? And this is symmetric. This is symmetric. Now, aij is decomposed in the symmetric part plus the anti-symmetric part. So aij, xi, xj is equal, no, aij is aij symmetric plus aij anti-symmetric times xi, xj. Now, the symmetric part, this is equal to aij symmetric xi, xj plus aij is skew-symmetric xi, xj. Now, we already did this before, so the anti-symmetric times the symmetric part, this will be 0. So, you see, the quadratic form aij xi, xj is unchanged if aij is replaced by its symmetric part, aijs. You see, look, aij over here, let's put a blue one to emphasize. See, aij, and here is right here. So aij xi, xj is equal aij symmetric xi, xj. So this is 0. Exercise, the quiz question number 2. If Pij is skew-symmetric and Qij is symmetric, then Pij, Qij is equal 0. So that's verify this, okay? Verify. Now, look, if I write, let's put Pij, Qij is equal lambda. Why lambda? This is a scalar. It's scalar. Why is it scalar? Because I is dummy and j is dummy. The same lambda I can put like that. For instance, PQ. Now Q will be PQ. You see the same lambda. You see, because I is dummy, P is dummy, J is dummy, Q is dummy. So I can put here J. I can put here J. Also I and I. So this is equal lambda. But since Pij is skew-symmetric, I can write that Pij is equal minus Pji, because Pij is skew-symmetric. Now, Qij is symmetric, so this will be plus Qji. You see, now this, you see there, will be Kij. This will be minus Pij. So this is equal minus Pij Qij. Now Pij Qij is equal minus lambda. You see, look, Pij Qij is lambda. Pij Qij is equal minus lambda. See, suppose lambda is 8. Pij Qij is 8. The same quantity, Pij Qij is minus 8. This is impossible. It's possible if lambda is equal 0. What I want to prove is this. Eij, partial derivative of ui with respect to xj, is equal Eij times Eij. First of all, this is a scalar quantity. This is a scalar quantity. Okay. Now, Eij is a strain displacement. This quantity we see in elasticity and also in fluid mechanics. Now, let's do this. Let's decompose partial of ui with respect to xj into its symmetric plus the skew-symmetric part. Now, I put here 1/2 partial of ui respect to xj plus partial of ui respect to xj. It's obvious because this quantity is the same as this. This plus this is 2 times this. Cancel this 2, it gives me this. Now, I add 1/2 partial of uj respect to xi minus 1/2 of partial of uj respect to xi. You see? Now you see that these 2 here can cancel. So I can combine this term over here. So partial of ui respect to xj is equal. Now this will be 1/2 partial of ui respect to xj plus partial of uj respect to xi plus 1/2 partial of ui respect to xj minus partial of uj respect to xi. You see, I just combine this term here with this one. You see, and this one with that one. Okay, the same. Now we can see here that this is a symmetric Sij. You see the symmetric part. Why? Because if I exchange I and j, this term will be the same. So this is equal Sji. Now this here is a skew-symmetric. Let's call like B or S star. S star asterisk Ij is equal minus Sji. You see, if I exchange j and I, this will be minus there. So remember that Eij, let's put blue one, Eij, see, this is symmetric Sij. Now, symmetric times symmetric. Now, symmetric skew-symmetric times symmetric will be 0. So this here is Eij. Now partial of ui respect to xj times the symmetric part, you see, this will be the symmetric part ij times eij. This is symmetric part eij. You see? Now eij, partial of ui respect to xj, I decompose in two parts, symmetric and skew-symmetric. Eij is symmetric, so the symmetric times the red one, the skew-symmetric, will be 0. So it will be Eij times Eij. Hence, Eij, partial ui respect xj, you see this Eij, I decompose partial ui respect to xj in two terms. Sij, which is Eij, okay, the symmetric part, plus the skew-symmetric part, which is there. Now, Eij, the blue one, plus Eij, the red one. So this here is 0, because symmetric times skew-symmetric is 0. Then Eij partial ui respect to xj is equal Eij, Eij.